So inferential stats, so where does this all come from? Well, I'm going to focus on frequentist statistics here, which is one kind of flavour of statistics essentially. Now it's largely informed by three statisticians, so Ronald Fisher, Jerzy Neyman and Egon-Pearson. Now these were all people who were concerned with trying to talk about probability from an objective standpoint. So instead of thinking about probabilities about your beliefs, for example, I think it'll rain with 60% chance tomorrow, or I think, for example, this football team might win the match at the weekend, something like that. Instead, they talk about probabilities in terms of objective frequencies of events out there in the real world. So instead of them trying to flip a coin and think, I think this will be heads with 50% chance, what they'll do is they'll try and figure out how often it should happen if you flipped a coin an infinite number of times. So let's say I've flipped a coin and it's 10 times and it's come up heads 7 times. I might ask, is this a fair coin? Now what I can do is I can estimate, well, how likely would it be for me to get 7 heads out of 10 flips, assuming I have some infinite number of coin flips out there. So let's say I flip this coin indefinitely. I want to see how often it is I get, say, 7 out of 10 heads here. If that's very unlikely, then I might use this as evidence that this is an unfair coin. If it's still quite likely, then I might not have enough evidence to reject the notion that it's a fair coin. Okay. Now this differs quite differently to Bayesian statistics, which is a different way of thinking about probabilities, where essentially you'll assign some probability to your data before you've even collected it. So here you might say, I think this is a fair coin with a certain probability. I'll observe some data and then I want to combine my predictions with my data to come up with an updated belief about the coin. Now this is a really interesting way to do statistics, but it's a bit too much to cover here. But if you're interested, I would suggest that you explore Bayesian statistics. So this frequentist approach to probability basically says that we can generate the probability of observing our data given a specific hypothesis. So let's say getting 7 heads out of 10 flips, given that I have a fair coin. This is what this PDH, the bar means. So what's the probability of observing my data given a certain hypothesis? Now that's one event, but we can assume from infinite events how many sets of coin flips that we could produce. So sets of 10 will produce this result. Now that's a meaningful measure of probability. What's really important that you don't do is to invert this probability. So we can calculate how likely it is to observe our data given that we have a fair coin. But this doesn't mean that the inversion of this number is the probability of our hypothesis. So the idea that you have a fair coin given the data that you have. That's more the Bayesian approach to doing things. Now you can think about why you shouldn't do this. So your probability of dying, given that you have your head bitten off by a shark, is 1. Pretty much everybody's going to die if that happens. But that's not the same as the probability of having your head bitten off by a shark, given that you're dead. Very few people die by getting their head bitten off by a shark. So given that you're a dead person, the probability that you had your head bitten off by a shark is pretty much 0. So you can't really invert these probabilities to think about them in the same way. So essentially our findings are interpreted as how likely are our data given a hypothesis. So you might be asking, well, what hypothesis do we use? How do we define this? Well, there's a reason why frequentist statistics is popular, is that it has this canned hypothesis that everybody can use. And this is what we call the null hypothesis. So essentially this Neyman-Pearson frequentist statistics, which is the way that most people do it now, is that it doesn't tell us how much we should believe in a hypothesis. Instead, it gives us a decision rule which, if we follow it, controls the rate at which we make incorrect decisions over time. Now, what I mean by this is that if I use the certain decision rules by this type of statistics, it might tell me that I have evidence against no effect to a certain degree. Now I can control the amount that I'll be wrong in making a decision by setting certain parameters in the statistics here, which we'll get to in a little bit as well. Now what we'll often do is we'll compare our data against the null hypothesis of no effect here. So for example, let's say I'm testing out a drug. I want to see, well, the null hypothesis in this case would be the effect of my drug is equal to the effect of my placebo. And I want to pit this null hypothesis of no difference against an alternative hypothesis, which could be effectively that the effect of my drug is larger than the effect of my placebo on some health outcome. Now, why do we pit it against this null hypothesis? Well, that's because this is the one that generally is the most costly hypothesis for us to reject. So we want to assume that the null hypothesis is true and find evidence against that if we can. We want to almost use this as a stringent kind of guideline that we need to try and get a lot of evidence against. So one way to think about why this is costly is that, well, let's say I want to test my drug against a placebo. Now, it's very costly if I find evidence against no effect here so that my drug actually works when that isn't the case. Because if my drug is actually in effect is not effective at all, then it might be that I'm going to cost people's lives by putting it out there, by putting it in production. And I might cost a lot of money to the company which produced this drug. So what we can do is, with this is what we calculate a p-value, which is a way for us to test our two hypotheses. So what's the evidence of my against this null hypothesis that I most care about? So this is essentially what frequentist statistics is largely concerned with, is testing your hypothesis. So you'll state your prediction. So I think my drug should have a larger effect than my placebo. And then I want to see whether or not I can reject that null hypothesis, which then implies that I can accept my alternative hypothesis. Now, you need to be careful in using that sort of terminology, but essentially what we use is when we reject the null hypothesis, we'll infer support for our alternative hypothesis. So if we have normally distributed data, we can assume that the data have a mean of 0 and some unknown variance. So what I mean by this is that generally there should be no effect in the population, but when you draw a sample from that population, you might get some random variation around this just due to sampling error. So I might have accidentally sampled some people who, for some reason, respond a little bit more to the drug than the placebo, or the placebo to the drug. You're always going to get some variation out there. So what we can do is determine how often we'll observe an effect as big or bigger than the one that we've observed if we were to repeat the sampling process from the same distribution indefinitely. So what I mean by this is we might run a test. So I might gather some people I give half a placebo, half of them get my real drug, and I observe if there's any difference in their health outcomes. Now, there might be some small difference there, and I want to know, well, is this a reliably small difference? Or I might find a big difference, and where I might think, well, there seems to be an effect, but I need to kind of be able to quantify whether or not I can support this claim. So what we need to do then is calculate the probability of observing an effect as big as the one we have if there was no true effect out there. Now, this is what we call a p-value. So it essentially is a measure of how unlikely are our results, or how surprising are our results if there was no effect in the population. So we can work out the p-value for a test by taking into account parameter estimates from a sample, such as maybe the mean or standard deviation and the number of observations that we have. So the best way to get estimates for dispersion for a hypothesis test can be to generate a standard error, which is just another variation on kind of quantifying dispersion in our data. Now we can use this mean, the standard deviation, and the sample size to determine a t-statistic, which, as I said earlier, is a standardized size of effect relative to variation in the sample. So what this means is that we want to see, well, yes, I might have a big mean size difference between the two groups I'm looking at, but if there's a lot of variation in the sample, you want your models to be able to incorporate that. So when there's a lot of variation, you need to be a little bit more uncertain about how big your effect is. When there's less variation and there's still a mean difference, then you might be more certain about making claims about differences between groups. Now, we know the shape of this t-distribution because we've looked at that earlier in this lecture. So from this, we can work out how surprising your t-value is, assuming there's no effect in the population. Now, finally, we get to working out our p-value. Now, luckily, this sounds like a lot of steps here, but luckily, when we kind of go about testing this in R or anything like that, any stats package, a lot of these steps are covered for you. All you need to put in is either your raw data or put in summaries of the data in terms of the mean, standard error, and the sample size, and it'll calculate the t-value and the p-value for you. Now here's an example of what t-values would look like, or the distribution of t-values under the null hypothesis. So what we should find is that, see, these red lollipops essentially are showing what size t-values we've got. So this one to the left-hand side of the 0, the dotted lines, is showing quite a small negative t-value. Again, the one to the right-hand side of that is, again, quite a small positive t-value. But the one even further to the right is a slightly larger positive p-value. Now what this means is that basically t-values close to 0 should be a lot more common than larger t-values, either in a negative direction or a positive direction. And essentially all this t-value is just how big is the difference between groups. So if you have group 1 minus group 2, or group 2 minus group 1, in both senses, if there is a difference there, then you can get both negative and positive results. So the sign on that t-value actually doesn't really matter. What matters is how big is the absolute value of the t-value. Now, under the null hypothesis, t-values should be either close to 0 or not all that far away from 0, essentially. Now, once you get essentially two standard deviations above or below this distribution, then we find that this is a really uncommon value if the null hypothesis is true. It's quite a surprisingly big effect. Now we use this then as our cutoff of what we would define as evidence to reject our null hypothesis of no difference between groups. Now if we found effects like this, then we might think, well, we seem to have an effect here. Okay, so our effect is big enough and reliable enough that we might have a real effect if we scaled this test up to the population. So then what we typically do is we'll use a predefined cutoff called alpha, which we calculate against our p-values. So what we want to look at is, what is our p-value, which is just a probability. So how likely are our effects under the null hypothesis? If that p-value is 1, well, it's pretty much always going to happen under the null hypothesis. If the p-value is below a certain cutoff, then we say we have evidence against our null hypothesis and in support of our alternative hypothesis. So what we might do then in psychology is we typically set this alpha threshold to 0.05. Now what I mean by this is that we care about p-values and we say that we can reject the null hypothesis if our p-value is below that alpha level of 0.05. So let's say I have a p-value of 0.01. This is below that cutoff of 0.05. But what if I always use this decision criteria of anything being below 0.05 is evidence in support of an effect, or evidence against our null hypothesis more accurately, then what this means is that I'll only ever have a 5% false positive rate. Now what I mean by this is that if I use this decision criteria in only 5% of every study I run, so if I do 1,000 studies, I should only have, say, like 50 false positive effects. If I do 100, I should have 5 false positive effects. That essentially I should only have a small number of false positives where I've said there is an effect when there really isn't one out there in the population. Now, if I want to be a little bit stricter about this, I might set my alpha level to something even smaller. Let's say 0.01. Now this means that if I always only interpret p-values below 0.01 as evidence against the null hypothesis of no difference, therefore supporting my claim that there might be a difference out there, then this means I only have a 1% chance of getting a false positive in the long run. But the problem with this is that means we need more convincing evidence to support our conclusion. So if we return to this plot here, then you can see that I might need even more extreme data than that right-hand green lollipop to support this cutoff of 0.01. Now all these p-values are is just, well, how likely are these dots on certain points on that x-axis? So if it's a big p-value, it's going to be a t-value close to 0. If it's a small p-value, it's going to be a high numbered t-value, which is far away from 0. Now again, hopefully this will make a little bit more sense when we look at actually interpreting some statistics further down the line. But essentially frequentist statistics uses inferential stats, and the point of this is to control how wrong we're going to be in the long run. So I'm only ever going to conclude that I have a difference between groups if I have strong enough evidence in support of that. Now, what I determine as being strong evidence is, well, if I assume there's no effect out there, how likely is my data under that assumption? If it's highly unlikely, then that seems to be evidence against there being no real effect out there in the population. So to control how often I'm going to be wrong about drawing inferences about a difference between groups in the long run, then I use an alpha level. Now this is basically going to be the number that we're happy to be wrong about in the long run. So we look at, is our p-value below a certain alpha level? If so, we reject the null hypothesis. If not, we fail to reject that null hypothesis and we can't see there's real difference out there. Now we can work out these p-values by combining the parameters that we have in our sample, and we can see how likely this combination of parameters is under the null hypothesis. So following this philosophy of statistics, we know that we'll only accept a false positive at a rate determined by our alpha level, and this is going to control the strength of evidence that we need to infer true effect. So linear regression, the rest of it. So with linear regression, what we aim to do is to learn the mean and the variance of some measurement by using an additive combination of other measurements. Now, essentially, you can think of this as the geocentric model of applied statistics. So it's used if used wisely, it can be very useful, but we shouldn't really read too much into it. You can only go so far with this model. So it can predict relationships that might be unrealistic. So you need to be careful in using your own domain expertise here. Now you can predict a linear relationship between one or more variables and a continuous dependent variable. This is where we use linear regression. Now, nicely, the predictor variables can be either continuous themselves or categorical. So I might predict somebody's height from their weight, so that would be a continuous predictor variable, or I might predict it by their gender. So I might use a categorical predictor variable there. Now, as I said earlier, most statistic tests or models, things like called t-tests and analysis of variance, mixed effects models are just extensions of this general linear model. So it's good for you to know how to use linear regression. So generally it takes this form of y, or some outcome, is represented by alpha, an intercept, beta, your slope, and you multiply this slope by whatever predictor variable you have, x, plus some standard residual error. So essentially what I mean by this is that you want to be able to predict where do the results start at on the x-axis of a plot, how steep is the slope that you'll draw along this line, so a line of best fit essentially, and essentially by what number do these points go up at, depending on what your kind of predictor variable is. Now it's important that we have this residual error here, because some scores will fall above and below your predicted estimations for how height should be predicted by, say, weight in this instance. Now the reason we do this is we don't actually want to fit a perfect model that perfectly predicts everybody's height given their weight. And that's because if you do that from your sample, then you're going to be overfitting your model to your data. Now what this means is that yes, it might capture the data in your sample very well, but if you then try and apply your model to new samples or to the general population, it's going to do a terrible job. So really we want to have a little bit of error left over in our regression. So that's why we have an error term. Now again, this formula should make more sense if we look at this plot that we'll get to in just a little bit. So a few things to bear in mind before we get to this is that the intercept, alpha here, is usually the point on the y-axis of a plot, which is the lowest value of x. So it's usually 0 if we're going to predict something here. The slope, or beta, corresponds to how much y increases for every increment that you have in x. And then the error is that residual variance, which I'll show you here. So here we've got a linear regression, or a linear model, which is predicting people's height from their weight. So as you see, generally the pattern is positive, so that there's this relationship in which as your weight goes up, so does your height. Now that makes a lot of sense in real terms. Tall people tend to be heavier than smaller people. Now let's say, how do we interpret the effects on here? Well, how am I going to accurately predict this, or how do I model this? Well, generally what these models do in linear regression is they use maximum likelihood estimation. So what I mean by this is I want to draw a line of best fit between the heights and weights, what is what these points represent, in which I'm minimizing the distance between all of the points and the line in the middle. Now, this is exactly what we have here. This is the best line I can get to accurately fit everybody's data when I consider it together. Now, it just turns out that when we use maximum likelihood estimation, it does quite a good job of predicting scores in the population as well. So then how do I interpret this plot? Well, this is a better way to look at it in terms of understanding what the intercept slope and the residual error is. So let's kind of reinterpret our model again. So if I have my outcome, height, is predicted by an intercept. So what's the weight at the point of 0 on the x-axis? I then have a slope, which says, well, how steep is the line? And I multiply that slope by weight. And then I add some residual error there, and that's how I come to everybody's individual height. So for example, here the intercept is approximately 80. So that's pretty much where that line intercepts 0 on the x-axis. So that's 80 is the height at the weight of 0. Now you can see that the slope, it's kind of hard to get your head around what this means, but essentially the slope is 1.85. So if we take 1.85 and times that by somebody's weight, then we should be able to accurately predict what somebody's height is going to be if we know what that intercept is as well. So let's say what's somebody's weight at 40 kilos here, then it should be around 150 centimeters in height. Now, what's somebody's weight at 80 kilos? Here it's going to be, let's see, 230 centimeters in height. So that seems to be what's coming out with this model here. Now we can see as well that we get some residual error here, which is where the dots aren't falling perfectly on the line. So this suggests then that what's going on with these dots is that we're not perfectly modeling a linear relationship between height and weight. Now, you need to be careful in interpreting this model in that it can also make predictions at people's heights at 0 kilograms. Of course, this is impossible. Nobody can weigh 0 kilograms. And it might make some really bad predictions when we have more sparse data at the top end as well. So if somebody's height is 100 kilos, it might make a pretty off prediction. So you need to always be careful in interpreting linear regressions. So then, when we fit a model using linear regression in any statistics package, the line of best fit in your parameter estimates can be estimated using that maximum likelihood estimation. From this, you're going to get parameters in your output, along with some stats that we'll talk about a little bit later. So the linear model essentially estimates the parameters associated with your intercept and the slope. So here, the intercept is going to be what is somebody's height at a weight of 0, and the slope is that increase in height for every unit increase in their weight. Now, what we get is some estimates of the error around this, which tells us, well, if I look at that slope, the best guess of it is 1.86, but the error around that is 0.167, both above and below it. Now we get this t-value and p-value as well, which we talked about a little bit before. Now what's going on here is that if I'm estimating the effect of this slope, this t-value test is saying, well, how likely is an estimate of 1.86, assuming that that's drawn from a normal distribution with mean of 0 and a standard deviation of 1. Now that seems to be very unlikely in this instance. This t-value, so it might have been drawn for a t-distribution actually, is showing that the effect is really unlikely. And that's exactly what that p-value recommends here. It says, well, these sorts of effects are, well, the probability of them is less than 0.001, assume that there's no effect out there. So the slope seems to be indicative of some true increase in height as people's weight increases as well. So then if we take all this together, then the linear regression is pretty much the heart of all statistical tests that you're going to do. So this then allows you to estimate parameters and test whether these parameters are surprisingly different from zero. Now it works by trying to predict an outcome based on some linear combination of any predictors that you have. So we've looked at the very simple case here where we'll just have one predictor and one outcome. Now we don't want to fit a perfect model to our data, otherwise it won't generalize beyond the data that we have in hand towards new samples. Now we've looked at how all models require an intercept, a slope and some error term. And when modeling, we need to be able to be mindful of how this is coded into the stats package that we're looking at to understand what these terms represent.